Hello, this is Mr. Mac, and this is the concept video for the rational zero theorem. Now, first of all, the rational zero theorem says that if you have a polynomial with integer coefficients, p of x is equal to maybe ax to the n plus bx to the n minus 1 plus so on plus, and we'll just use c down here as the constant. Then, and a, b, c, all the others, the coefficients are integers. Then the rational zeros of p of x must be in the form I can do this. Oh, come back. Must be in the form of p over q, where, plus or minus p over q, where p is a factor of the constant, in this case c, and q is a factor of the leading coefficient, in this case a. Now, I think it probably would be best if I showed you an example. So imagine p of x is equal to 6x to the fourth plus 25x cubed minus 7x squared minus 104x minus 60. Now, if, and there are a couple of different questions that you're going to be asked. One question, and this is kind of an important question to pick up on, is list all the possible rational zeros of p of x. Now, if they ask us to do that, and you got to look for the word possible, list all the possible rational zeros of p of x. If that's the case, then what we need to do is we need to find all the fractions where the numerator is a factor of 60. That comes from here. And the denominator is a factor of 6. That comes from here. Okay, now, to do that, probably the easiest way is to start out listing the factors of 60. 1, 2, 3, 4, 5, 6, 7 isn't a factor, 8 isn't a factor, 9 isn't a factor, 10 is, and 12, and 15, and 20, and 30, and 60. And then list all the factors of 6. 1, 2, 3, and 6. So then, what we do is we start out. Let's use the 1 for the denominator. We get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 12, plus or minus 15, plus or minus 20, plus or minus 30, plus or minus 60, comma. Now we'll go back and we'll use 2, plus or minus 1/2. Now, I don't have to write plus or minus 2/2 because I've already written that as 1. Plus or minus 3 halves. I don't have to write 4 halves. I do have to do 5 halves. Plus or minus 5 halves. 6 halves I've done is 3. 10 halves I've done. 12 halves I've done. Plus or minus 15 halves. Plus or minus 20, 30, and 60 halves I've already done. So now we'll go back and we'll use 3 plus or minus 1/3 plus or minus 2/3. Now, plus or minus 3/3, we've already done that one. Plus or minus 4/3. Plus or minus 5/3. 6/3 have done, plus or minus 10/3. 12/3, 15/3, plus or minus 20/3. 30/3 and 60/3 we've already done. 30/3 is 10. That's there, and 60/3 is 20. That one's already there. Now we'll go back and we'll use 6. That's plus or minus 1/6. 2/6 I've done. 3/6 I've done. 4/6 I've done. I haven't done 5/6. Plus or minus 5/6. 6/6, of course. 10/6 is 5/3. 12/6 is 6. Well, it's 1/2. It's 2. I've done that one. 15/6 is the same as 5 halves. We've done that one. 26 is 10/3. We've done that one. 36 is 5, and 66 is 12. We've done that. So we're finished. There's the list of possible rational zeros. Now, they're not all zeros, but the idea was when the mathematicians originally discovered this cut the number of possible rational zeros from an infinite number down to a finite number. Now, it would depend, of course, on how motivated you were to find the zeros of this polynomial. But nowadays, with technology, it is a lot easier. Now, what we can do with technology is we can go ahead and we can put this polynomial in the y equals register. In other words, I'm going to put 6x raised to the 4th plus 25x raised to the 3rd minus 7x squared minus 104x minus 60. Now, there's a number of things we can do here. One way, we can just graph this thing and kind of see where we're expecting zeros and see if we can't kind of figure out where they are. Now, it looks like there might be a 0 at 2. There might be one at, well, it's somewhere between 0 and -1, maybe -2/3. Looks like there might be a 0 around -2 maybe. And maybe, let's see, 1, 2, 3, maybe -3. Maybe not -2, I'm not sure. But anyway, now that we've found these, there's a number of things we can do. First of all, if you press trace, the calculator will actually give you the y value if you type in an x. See, I type in x equals 2 and press enter, and it's saying, yes, 2 is a 0. I type in -3 and press enter, and it says 0, so -3 is a 0. I type in -2/3 and press enter, and yes, -2/3 is a 0. -2, not so much. Okay, so -2 wasn't a 0, but we have 3 zeros. Now, the corollary to the fundamental theorem of algebra tells us that since this is 4th degree, we're expecting 4 zeros. So what we should do here probably is divide these into the original polynomial and then use the depressed polynomial to get additional zeros. So let's go down here and let's do some synthetic division with this polynomial. So first of all, let's go with -3. I find that if you use the biggest number you can, I mean value-wise, absolute value-wise, that the numbers get smaller quicker, and that's nice. 6, 25, -7, -104, -60. All right, so now let's go ahead and do this. We bring the 6 down. 6 times -3 is -18. So what does that give us? That gives us 7, I believe. 25 plus -18 is 7. Times -3 is -21. That gives us -28 down here. -3 times -28 is positive, well, 60, positive 78, I think. And so we've got 22 and 4, which is 26. 26 times -3. No, that's not going to be right. I've made a mistake here someplace. Let's go back and do this again. I'm not quite sure what's going on here. I may have to use a calculator because I've made some kind of a mathematical mistake. This one's supposed to work. Did I do that right? 6, 25, -7, -1, 4, -60. Yeah, okay. So now, second quit. This is 6. -3 times 6 is -18. Now let's just check. 25 minus 18 is 7. -3 times 7 is -21. -21 plus -7 is -28. -3 times -28 is 84. Okay. And -104 plus 84 is -20. And okay, -3 times -20 is 60. And when we add, we get 0, which is what we were expecting. All right, now, for the second round, oops, what's going on here? Let's use the -2/3, because there's something I'd like to show you here. -2/3. Now, I'm going to go ahead and just use the numbers to the left of this up and down line here. So bring down the 6. -2/3 times 6 is -4. 7 plus -4 is 3. -2/3 times 3 is -2. That gives us -30 down here. And -30 times -2/3 is 20. And we get 0. Now, at this particular point, let's take a look at what we've got. We have this 0 right here tells us that x plus 3 is a factor. Now, this 0 tells us that x minus negative, or x plus 2/3 is a factor. And these numbers here tell us that 6x squared plus 3x minus 30 is a factor. Now, one of the things that happens when you're using a fractional 0 is you get this binomial that has a fraction in it. Now, if it's a 0 and you had integer coefficients to start with, what's going to happen is over in this polynomial, there's going to be a factor of 3 that you could take out of this one. In other words, we have 3 times 2x squared plus x minus 10, and we could multiply that 3 by this binomial, and what will happen is this will become x plus 3. This becomes 3x plus 2, and then we have 2x squared plus x minus 10. And I'm going to pause here for a minute. And I'm back. Now, what I was saying was that you can, if you've got a rational 0 that's a fraction, you can use synthetic division, and then what you do is you take the bottom number in the fraction, 3 times x, minus the numerator, so that's 3x minus -2, or 3x plus 2, and then just divide the numbers, these numbers here, by the denominator, and that will give you polynomials that work. Now, see, what we've got now is we've got a depressed polynomial of second degree. We're expecting, by the fundamental theorem of algebra, with a fourth degree polynomial, for there to be 4 actual zeros, and the other 2 are going to come from this one. So we're going to try to factor 2x squared plus x minus 10. And the master product of that one is negative 20, and 2 numbers that multiply to give negative 20 and add to give positive 1 are negative 4 and positive 5. So what we'll do is we'll write 2x squared minus 4x plus 5x minus 10. Grouping the first 2 and the last 2, we can take a 2x out here, we have x minus 2. Take a 5 out here, we're left again with x minus 2. So we get x minus 2 times 2x plus 5. So all told, this polynomial factors into x plus 3, 3x plus 2, x minus 2, and 2x plus 5. Now, if we set each of these binomials equal to 0, they'll each give us a 0. X plus 3 tells us x is negative 3. 3x plus 2 tells us x is negative 2/3. X minus 2 tells us that x is equal to 2. And 2x plus 5 tells us that x is equal to negative 5/2. So the zeros of this polynomial are negative 3, negative 2/3, 2, and negative 5/2. So what we've done is we have used a number of the different skills that we've learned up to this particular point. We define the actual rational zeros of p of x. Now, one more thing I would like to mention is that sometimes some of the zeros are not rational, but if we can get down to a depressed polynomial that's a quadratic, then we can get the irrational and even non-real complex zeros from that. Here's an example of that. If we let p of x be equal to x cubed minus 7x squared plus 17x minus 15, and we want to know all the zeros. Now, if it just said find the rational zeros, this one's only going to have one rational zero, but let's say the directions say find all the zeros. Now that means including irrational, including non-real complex zeros. Well, what we need first of all is we need at least one zero to be rational. And so what we're going to do is we're going to put this polynomial in there, x cubed minus 7x squared plus 17x minus 15, and we'll graph it. And notice it looks like there's a 0 at 3. So let's go ahead and act as if there is a 0 at 3. And 1, 3, negative 4, negative 12, 5, 15, there we go, 0. So we get x minus 3 as a factor, that comes from here, and we get x squared minus 4x plus 5 as the other factor. Now if the directions are find all the zeros, you would first say, well, can x squared minus 4x plus 5 be factored? And you ask yourself, are there any numbers that multiply to give positive 5 and add to give negative 4? And there aren't. So next we're going to use the quadratic formula with this. X is equal to 4 plus or minus the square root of 16 minus 20, that's 4 times 1 times 5, all over 2. Now 16 minus 20 is negative 4. The square root of negative 4, we pull out the I, square root of 4 is 2, so we get 4 plus or minus 2i over 2. Now folks, there is a factor of 2 in the numerator, and there's a factor of 2 in the denominator. I do expect you to find those. So now what we've got is the zeros are 3 and 2 plus or minus I for this one. Now, in this in these exercises, you're going to be given polynomials, and you need to pay attention to the directions. Sometimes they will just say, list all the possible zeros. When it says that, this is what I'm expecting. When it says find all the rational zeros, I'm expecting the rational zeros to be found. And when it says find all the zeros, I'm expecting all the zeros, including irrational and non-real complex zeros, to be found. Now, you're going to get a chance to practice this, and there are solution videos showing you how to do all the odd-numbered problems, and I heartily recommend that you watch all of those things and enjoy. And this ends the concept video on the rational zero theorem.